Hi folks, I'm going to be talking about our paper, Near Optimal Schedules for Simultaneous Multicasts. This is a collaboration with my advisor, Bernhard, David, who's a postdoc at Stanford, and I'm Ellis. Here are some books so you know that I'm smart. So let me just get right into it. So the general motivation for our work is that of content delivery. So imagine for a second that you're some sort of content provider, say Netflix, and you would have different content stored in different databases around the world. So maybe you have different shows stored in different places around the world. And you, of course, have all of these customers, and different customers want to watch different shows. But at the same time, the internet is sort of only one network. So you have to serve all of these different demands from your different databases to different people all over the same network. So different people will want to watch different shows, and sort of the challenge here is that you have these links in the network that have to be used for different content. So there's sort of competition for different content over the bandwidth in your network. So generally speaking, like the goal of this work is to understand how to efficiently and simultaneously deliver different data in a network where you have bandwidth constraints in your network. All right, so how are these sorts of problems normally formalized? Well, first, the model of communication that people typically study is the so-called store and forward model. So here, as usual, when studying distributed computing, we imagine that a network is modeled as a graph where nodes correspond to computers and edges correspond to links between computers. And in the store and forward model, we imagine that time proceeds in synchronous rounds. And in these rounds, nodes have packets, which I'll use like little letters to notate. And we model these bandwidth constraints by saying that at most one packet crosses an edge in any particular round. So what does communication look like in a store and forward model or in a store and forward network? Well, in one round, nodes will exchange packets. Maybe next, like both of these packets at the top want to cross the same edge, but because of these bandwidth constraints, it'll take us 2 rounds. Okay, so that's a store and forward model. Now, how do we formalize this problem of content delivery? Well, we can formalize it as what I'll call the simultaneous multicast problem. So here, we imagine that we're given a store and forward network, but in addition to the store and forward network, we've designated some subset of the vertices as so-called routes. Each of these routes has some packet, and along with each route, there's a corresponding tree. And I'll notate the packets, trees, and routes according to in different colors according to which ones they correspond to. Okay, and now when we're trying to understand how this content delivery problem, what we want to do is we want to understand the length of the schedule that minimizes the total number of rounds so that the leaf of each tree gets the packet of its parent. And to be clear, we allow ourselves to duplicate these packets when the tree branches, but we are subject to these bandwidth constraints of the store and forward network. So let me just illustrate what a schedule might look like. So in round 1, nodes exchange packets. Notice that, again, we have at most one packet crossing an edge, and this red packet was duplicated where the red tree branched. And nodes keep exchanging packets, and they keep getting passed along edges until at the end of the day, what we have is we have every leaf of each tree has the packet of its corresponding root. Okay, so that's the simultaneous multicast problem. And now when studying these kinds of problems, there's 2 sort of parameters that people care about. So the first parameter is the so-called dilation. And this is just the maximum over all of our trees of the depth of each tree. So in this example I just gave, the dilation will be 7 because if you look at this one green tree, there's a root to leaf path that consists of 7 edges, and that's the longest root to leaf path among all of our trees. Now, the other parameter that people study is the so-called congestion. And this is just the maximum over edges of the number of trees that edge participates in. So in this example, the congestion would be 3 because this edge that I pointed out here has all 3 trees using it, and any edge is used by at most 3 trees in this example. So one sort of like easy to see piece of folklore is that the length of the optimal schedule, which I'll notate with opt for the rest of the talk, is always at least C plus D. Now, why is that? Well, if you think about the dilation, then in any given round, the path which defines this dilation has at most one packet, or you make at most one edge of progress along this path. So you're going to need at least dilation many rounds. Similarly with congestion, if you think about the most congested edge, any feasible schedule has to have at least congestion many packets cross it, but at most one crosses it per round because of our bandwidth constraints. So both congestion and dilation are lower bounds on the length of the optimal schedule, and just by sort of standard asymptotics, congestion plus dilation is also therefore a lower bound. And let me just emphasize the following point, which is when these packets travel, they're only allowed to travel along their corresponding trees. So for example, in this instance that I just gave, the green packet can only travel along the edges of the green tree. Okay, so let me just put these parameters up in the right-hand corner here so we don't forget what they are. Now, what's known about these sorts of scheduling problems in store and forward networks? Well, a very well-studied special case of this simultaneous multicast problem that I just gave is the simultaneous unicast problem. So this is simultaneous multicast, except each of these trees is actually a path. And this was very famously studied by Leighton, Maggs, and Rao in 1994. And they showed the very surprising result that there always exists a simultaneous unicast schedule whose length is at most order C plus D. So this matches this really trivial lower bound that I was able to tell you in like 2 minutes. And if you ever take like a randomized algorithms class or maybe like a randomized grad algorithms class, you might see this result because it's a very nice application of the Low-Lush-local lemma. Okay, now what's known about this simultaneous multicast problem that I just described? Well, again, we have this trivial focal or lower bound of C plus D, but we also have sort of a trivial focal or lower bound of C times D. Where does this come from? Well, you can imagine that we could take our rounds and sort of group them into so-called meta rounds, each with C rounds in them. And now in each meta round, we know that there'll be at most one packet trying to cross an edge, or sorry, there'll be at most C packets trying to cross an edge, but since we've allocated C rounds to this meta round, we can always move all of our packets along any given edge in a meta round. And so then you only have to pay like D total meta rounds and you end up with a schedule of length C times D. Now, a little bit more involved, there's an upper bound for the multicast setting that kind of follows immediately from some observations in Leighton, Maggs, and Rao that shows that the length of the optimal schedule is at most C plus D times log n. Okay. Now, what makes studying simultaneous multicast even more interesting is there's actually a case which generalizes both the unicast and the multicast setting, which has been studied. In particular, unicast sort of correspond to paths, multicast correspond to trees. And if you want to just go like one level of complexity up in terms of the structure that you're scheduling over, you might go to directed acyclic graphs. And this kind of corresponds to scheduling arbitrary algorithms in a store and forward network, just because you never sort of need a cycle of information being passed in an algorithm. And Mose and Ghaffari studied this in a PODC 2015 paper and showed the surprising result that this C plus D times log n is actually tight for scheduling of DAGs. And this won him the PODC 2015 Best Student paper. So given the history, there are two very sort of natural questions you might ask. You might ask, like, multicasts lie between unicast and DAGs. So are they on the sort of unicast side in terms of complexity? Like, can we get a C plus D length schedule for multicast? Or are they more on the DAG side? Like, is this C plus D times log n that's required for DAGs also required for multicast, i.e. trees? And the answer in what we show in our paper is, I think, the slightly surprising result that it sort of depends. Okay, so let me tell you about our results and our main theorems and the sense in which it depends. So the sense in which it depends is, it depends if the length of your optimal schedule is allowed to be a function of n, the number of nodes in the network. So if you just want to understand the length of a schedule as being a function of the congestion and dilation, what we show is that for simultaneous multicasts, the length of the optimal schedule is always at least C times D. So this matches this trivial upper bound of C times D, which I laid out using kind of meta rounds. So if you're just sort of going to plot the complexity of these scheduling problems on like a line, on the one side, you have unicasts that always require C plus D and that's tight. And on the right side, you get multicasts and DAGs that always require and are possible to schedule using C times D. And this lower bound of C times D actually wasn't even known for the DAGs case before our paper. Okay. But the next thing is, well, what if I allow the length of my optimal schedule to depend on n, the number of nodes in the network? Does this change the sorts of bounds that are possible? And what we show is that in this case, you necessarily have to pick up an additive log n. And basically this is tight. So there always exist schedules that pick up an additive log squared n. And I think what's particularly cool about this is like, now if you were to sort of plot the complexity of unicasts, multicasts, and DAGs, where the length of the optimal schedule is allowed to be a function of n, you have this nice smooth interpolation between these problems. So all the way on the left, you have sort of a C plus D in unicasts as per these results of Leighton, Max, and Rao. Then you have our results, which show that you can get away with only picking up an additive polylog, and this is somehow necessary for multicasts. And then when you go to DAGs, you necessarily pick up a multiplicative polylog. So these problems are all sort of cleanly separated in terms of how long the optimal schedules are. And the last thing we do is we give some both centralized and distributed algorithms. I'm not going to talk that centralized and distributed algorithms for these to find these schedules of length C plus D plus log squared. I won't talk too much about that in this talk, but if you're interested, check out that paper. All right, so for the rest of the talk, I'm going to try and just like sketch our main results and how we show them. And I think something that's kind of nice about this paper is everything is simple and elementary enough that I can give you all basically all of the main ideas for this paper. And I think probably after this talk, hopefully you could go and like recreate the proofs if you wanted to. Okay, so first I'm going to talk about our upper bound of C plus D plus log squared. And our upper bound is going to use this idea of random delays and heavy path decompositions, which I'll describe. And then I'm going to sketch our lower bounds, both the C times D and the C plus D plus log squared, or C plus D plus log n lower bound. Okay, so let me talk about the upper bound, and let me talk about this idea of random delays. So consider the following instance of simultaneous multicast. And if you were to just look at this problem, you notice that like there's one edge that's congested to extent 3. So you might imagine that like in the length of your optimal schedule, you should somehow end up having to pay this congestion. But this kind of funny thing that happens in this example is if you start just greedily forwarding messages along their respective trees, you'll notice that this edge, even though it's congested to extent 3, is never actually backed up. There's never multiple messages waiting to cross the edge. So this idea of random delays is like, what if we just sort of randomly delayed when we actually forwarded messages to encourage this low, what I'll call effective congestion? Like, even though in theory, maybe a lot of messages might eventually have to cross an edge, maybe we can sort of smooth out the time that those messages show up to an edge by adding random delays so that there's never too much contention along a single edge. So let me make this random ideas delay a little bit more concrete with another motivating example. So here's an example where if we just ran this greedy schedule where we started just forwarding messages whenever we can, we would have 2 messages collide at a node, and in particular, in the next round, they both want to cross the same edge. So now, just imagine for a second that we added a random delay to when we started this greedy schedule, which you can equivalently conceptualize as adding a prefix of sort of fake nodes to each of these routes, and then starting all of our messages at the beginning of these fake prefixes. So then we start greedily forwarding. We're imagining that they're moving along these fake prefixes, although in reality, they're really just sitting at their respective routes. And what we'll see is that even though we have an edge congested to extent 2 and an edge congested to extent 3, there's never any contention at the edge, just because we sort of randomly perturbed when we started sending our messages. All right, so that's the idea of random delays. Now the second idea behind our upper bound is that of heavy path decompositions and reducing multicast to unicasts. So recall that Leighton, Max, and Rao showed that we can very effectively schedule simultaneous unicasts. Like we can schedule unicasts in times C plus D. But if you think about a tree in the multicast setting, like a tree is really just the union of a bunch of different paths. So a very simple idea, and the idea that we use in our algorithm is, let's just decompose our multicast into a bunch of unicasts, okay? So pictographically, we'll take each of the trees corresponding to our multicasts, like this tree I've drawn here, and we'll separate it into a bunch of little paths. And then what we'll do is we'll sort of just work our way out in a BFS manner from the root of this tree and solve a series of unicasts. So this multicast tree would sort of contribute 2 paths to the first unicast instance that we solve. Then it would contribute another 2 paths to the next unicast instance that we solve, and so on as we work our way out in a BFS manner until we've successfully broadcast to all of the nodes in all of our trees. Okay. So the next natural question is like, well, if you're going to take each of your multicast trees and break it up into a bunch of unicasts, like what's the right way to break your multicast up into a bunch of unicasts? And fortunately for us, there's this very elementary and well-known result of Slater and Tarjan from way back when that shows that given any tree, you can partition the edges of that tree into a bunch of paths so that if you look at any root to leaf path, you'll intersect at most log n of the paths in your decomposition. So pictographically, what does this look like? Well, you start with some arbitrary tree. You apply your heavy path decomposition, it breaks your tree into a bunch of paths. So here I've notated each path with a different color. And now, if you look at any root to leaf path, this path will intersect at most log n of your heavy path decomposition paths. So in particular, in this example, the number of colors on any root to leaf path is going to be at most order log n. All right, so coming to our algorithm and how we combine this idea of heavy path decompositions and random delays, what do we do? Well, for each of our multicast trees, we'll first just take a heavy path decomposition. And then what we'll do is we'll sort of separate each of the paths in our heavy path decomposition every log n often. So sort of break up each of these paths into even more paths, which will guarantee that each of the unicast instances that we solve will have dilation log n. And again, this is just because we're sort of cutting our heavy path decomposition paths every log n often into sort of subpaths. Okay, now how do random delays come into this? Well, we're going to just add a random delay of a bunch of fake unicasts at the beginning of each of our trees. In particular, we'll add like a uniformly random number of fake unicasts in C over log n. And just by sort of standard Chernoff and union bounds, it's not too hard to see that what this will do is it'll guarantee that each of these unicast instances that we solve will have congestion at most log n. Okay, so why is this nice? Well, we're solving a bunch of unicast instances, and each of the simultaneous unicast instances that we solve will have dilation log n and congestion log n. Now, by the result of Leighton, Maggs, and Rao that shows that you can solve these problems in time order C plus D, we can solve each of these unicast instances in time log n. Okay. Now, the next thing to consider is like how many unicast instances are we going to have to sort of sequentially solve in order. And it's not too hard to see that the total number of sequential unicast instances that we'll have to solve is C over log n plus D over log n plus log n. So the C over log n just comes from the fact that we're adding up to C over log n fake unicasts to the beginning of each of our tree. The D over log n comes from the fact that we're cutting our paths log n often. And this additive log n comes from this property of heavy path decompositions, which says that if you look at any root to leaf path, you intersect up to log n of our paths. All right. So again, each of these we can solve in time log n. So just multiplying log n by the number of them that we have to sequentially solve, you end up with our upper bound of C plus D plus log squared n. Okay, so I gave kind of a sketch of our upper bound of C plus D plus log squared n using this idea of random delays and heavy path decompositions. I'm next going to touch on our lower bound sketch, both of the C times D and C plus D plus log n lower bounds. And the construction will actually be the same for both of these things. So let me talk about the C times D lower bound construction. So think about an edge and imagine that it's used by C trees. So here C is like 3. And just by virtue of our bandwidth constraints, we know that one of the packets that want to cross this edge is going to need at least C rounds to cross it, where maybe for a second, just imagine that each of these packets start at the top end of this edge. Okay, next, just imagine that you'd had C such edges. All right, so we know that for each of these edges, there's going to be some packet that's going to require C rounds to cross that edge. Now, if we somehow just magically knew which of these packets were the slowest packets along each of these edges, like which were the ones that were going to get delayed by at least C, then we could sort of combine these into a new edge. In particular, imagine for a second that the packet on the far right, as I've drawn it, of each of these edges is the one that's going to be most delayed. Then we'll get a new edge that looks like one of the edges that we started with, but every packet will have accumulated a delay of at least C. So in this example, in the first C rounds, these faster packets will go off and do whatever, but then our slower packets will then cross these edges and arrive at this new edge that we created, where this new edge is just like one of the edges that we started with, but every packet shows up to it after at least C rounds. All right, so this is kind of just like a nice, useful gadget from elementary observations. Now, what's the problem with what I'm talking about, and why can't we come up with a gadget like this? Well, we don't actually know which of the packets are the slowest packets along any given edge, right? And in particular, this gadget that I've described so far doesn't use the fact that we're working with trees and not paths. It doesn't use the fact that these trees branch where paths do not branch. And we know that for paths, we can get a C plus D. So we shouldn't expect to have to incur a C times D if we're like just cobbling together a bunch of these gadgets. So how do we get around the fact that we don't actually know which of these trees are the slowest? Well, we're going to use the fact that trees, unlike paths, branch to just guess which are the slowest, okay? So before we were like, well, maybe it's the ones on the far right which are the slowest, but we might say like, well, maybe it's actually these other three that are the slowest, or it's these other three that are the slowest. And we could imagine basically taking all possible guesses of like which are the slowest packets along each of these edges. And what do we know at the end of the day? Well, we know that one of our guesses, regardless of whatever the schedule is, will actually have successfully guessed which are the slowest packets. All right. Now, then what do? Let me just hand wave for a second. We recurse. So like we did all these guesses for all these packets, and we end up with one of these edges that look like the edges that we started with, except now everything has accumulated a delay of C. And now we're just going to take a bunch of those delayed edges and like stick them together, and then we'll end up with a delay of 2C and 3C and 4C and so on. And if you think about this, what you'll end up with is like an instance of simultaneous multicast where you always need basically C times D rounds to solve. Okay, so let me also just point out that the construction for C plus D plus log n, the lower bound that we give, is also the same construction, but you just have to sort of think about the dependence on n when you're doing a construction like this. Okay, so that's really like the main parts of my talk. Let me just quickly summarize. So what do we show in our work? We show that if the optimal schedule is only a function of C and D, then multicasts and DAGs basically have the same complexity, and their complexity is C times D. But if we allow for the optimal schedule to be a function of C, D, and N, then you get this nice separation between unicast, multicast, and DAGs, where for unicast you have a C plus D. When you go to multicast, you pick up an additive polylog, and then by previous results, when you go to DAGs, you pick up a multiplicative polylog. And we also gave algorithms, which I didn't talk about. Okay. So I talked about the main proof ideas behind these bounds. So for the upper bound of C plus D plus log squared, the idea really is to just reduce multicast to a bunch of unicasts. And the way that we do that is we use random delays to ensure that the unicasts have small congestion, and we use heavy path decompositions to really break our trees up into paths that will correspond to simultaneous unicasts. Now for the lower bound, I kind of sketched this idea that you can guess which packets are most delayed by using the branching of trees, and then sort of recursively combine together these like most delayed packets into more and more and more delayed packets. So I think really the main question in future work is to tighten this log. So I drew this like line before with the complexity of multicast of C plus D plus some polylog, but really the picture should be something more like this, where we have a separation between our lower bound and our upper bound. I think to me, it really feels like we're paying the same log twice in our upper bound, and the right answer probably should be C plus D plus log n. So it would be nice to just close that gap. And I think it's a good question. I think the other thing which might be interesting is studying the version of simultaneous multicast where you're allowed to actually choose the trees. So, simultaneous multicast, as I described it, was this problem where you're given like a root and you're given a tree for each root, and each root has some packet. But you could imagine that you're given a root, you're given a collection of leaves, but then your algorithm is allowed to choose which of the trees that it wants to send its packet along to those leaves. And people have studied this in the simultaneous unicast setting. There's this kind of famous paper of Srinivasan and Teo that does that. I think it would be cool to do that for the simultaneous multicast setting. So this sort of corresponds to the so-called depth-bounded multicast congestion problem. All right, so thanks for your time, and I hope to chat with some of you at ICAP.